for that reason, I'll be looking in particular at safety aspects and regulation of such systems and how we would test those systems. And what you can see here, we're going to be talking about how systems learn, in which case they need good training sets. And one of the problems that we'll see a bit later is that if we choose the wrong training set, then we'll get the wrong results. It's very easy to train our artificial intelligence to actually give us the wrong things. Here, well, anyone guess what this is? Could be used as a training set for? Cats. Are they all cats? Well, actually, according to Google, these are all cats. And now I know that there are many cats in the world that I don't want as a pet, because some of these just would look too scary if I woke up in the night and saw it looking at me. So we choose our training set for what we want. If I want a cute cat, this is not a good training set. If I just want to identify the complete range of cats, it's fine.
네. 우선 오늘 초대를 해주셔서 대단히 감사하다고 말씀을 해주시고, 오늘 자율 시스템에 관련돼서 주된 포커스는 자율 시스템의 안전에 대해서 주로 말씀을 해주신다고 하십니다. 그래서 우선 제일 처음에 첫 번째 보시고 계시는 슬라이드는 자율 시스템을 트레이닝하기 위해서 필요한 세트들 중에 여기는 지금 고양이에 대한 세트를 보여주고 있습니다. 개 중에는 상당히 귀여운 것도 있고 아닌 것도 있지만 우선 고양이를 트레이닝하기 위해서 필요한 세트를 보여주고 있습니다.
Okay, so I'm going to look at autonomous systems in general, but my main involvement has been with autonomous cars, and so I'm going to use that as an example. Now I've got to try and work out if I can use. Oh, that looks possible. There we go. This is Argentina. Of course, we're not quite at this stage yet, but you can imagine if we have autonomous cars and everything's controlled by computer, we could walk across the roads and be absolutely safe without looking. So the cars get really close together. Journey times get much shorter.
네, 보셨던 예제는 아르헨티나의 예제였고, 아직 저 단계는 되지 않았지만 실제적으로 완전 자율주행 자동차가 되게 되면 저와 같이 목적지까지 훨씬 빨리 도달할 수 있는 그런 결론을 얻을 수 있다고 말씀하고 계십니다.
So what I want to cover for the rest of the afternoon is generally introduce the idea of self-learning systems that will work autonomously. So I'll explain what I mean by those systems, give some examples. Many of the autonomous systems now are based on machine learning. So I will explain how machine learning works, high level. I apologise for the people who already understand it fully already. But if I explain it at a high level, that allows me to identify where we can do some testing. So where, if we're testing such a system, we can actually apply it to the machine learning. I'll identify some problems with non-deterministic systems, because nearly all of these systems use probability. Therefore, they change their results over time, even with the same inputs. And then, if it's a machine learning system, it is generating a neural network. So I'll look at how we can do black box and white box testing of these neural networks. Because if we're going to use them in a safety-critical, safety-related environment, then we have to consider both black and white box testing. And if we're going to use these systems in the real world, the number of scenarios that they're actually going to encounter and have to cope with is going to be phenomenally large. Therefore, we will not be able to test them all on the real streets of Korea, America, UK, wherever. We have to test them in virtual environments. And finally, I'll look at a suggestion. I'll provide a suggestion that if we're going to move these systems out into the real world, then government should really introduce regulations, which will be good for some countries, and some countries will think that is okay, but some countries, like perhaps the US, will think regulation is bad because they have a businessman as president who thinks innovation should drive everything.
네, 그래서 오늘 설명드린 목차는 지금 보시는 것 같고, 자율 셀프 러닝 시스템에 대한 거하고 머신 러닝에 대해서 개괄적으로 설명을 해주실 거고, 대부분의 이런 시스템이 확률을 기반으로 하기 때문에 비결정적인 시스템이 가지고 있는 문제하고, 그 다음에 이제 이런 시스템을 위한 블랙박스하고 화이트박스 테스팅에 대해서 말씀을 해주실 거고, 실제 이런 시스템을 실제 환경에서 전부 테스트하기가 불가능하기 때문에 가상 테스트 환경의 필요성에 대해서도 얘기를 해주실 겁니다. 그리고 마지막으로는 이제 정부에서 이런 시스템을 위해서 해야 되는 규제나 기타 제도에 대한 박사님의 생각을 말씀해 주실 예정입니다.
Okay, so I want to introduce the idea of autonomous self-learning systems, and in fact, when we look at the definitions, what we'll find is that most of the definitions we use now, as soon as we say autonomous, we already mean that they're going to be self-learning.
네, 그래서 자율 시스템이라고 하는 거는 기본적으로 밑바탕에는 셀프 러닝 하는 시스템이라는 게 기본적으로 깔려 있다고 요즘에 얘기하고 있습니다.
So if we look at a definition, a dictionary definition of autonomy, autonomy is the capacity to make an informed, uncoerced decision. So a decision where we're not forced to do something or even prompted to do something. And there are a number of autonomous organisations around the world which are free from government control. So we have things like the International Atomic Energy Agency, which is free from any government control. World Trade Organization, again, free from government control. So if it has no control, it can make decisions on its own, presumably based on its mission. In which case, for an autonomous system, the autonomous system is going to make decisions on its own, but of course we have to give it a mission. So the definition down here, so it's a smart or intelligent system. So by that, I'm saying it's not just an automated system. We have many, many automated systems where we tell it, we program it what to do, it looks at the inputs, and it does the same thing every time. It's completely deterministic. When we're talking about autonomous systems, we're looking at a level above that. So we're looking at it having some intelligence to make those decisions, but it has to achieve delegated objectives. Now, if you don't give these systems delegated objectives, if you don't tell them what they're supposed to be doing, then they will start doing unusual things. The Americans last year lost one of their large unmanned drones because they forgot to tell it what to do if it lost contact with the ground. And they tracked it on the radar because they had no control of it at this point. And they were wondering what it was trying to do, because it should have been doing one of three things, I think. One of them was to fly back to its original base, which would be a useful thing to do. One of them was just to land at the nearest airfield it could find, and I can't remember the third thing. It was doing none of those three things, as they could tell, but when they actually asked, they found that no one had told it what to do. And they then worked out maybe it was flying back to the base the last time it was properly programmed and told what to do, which was over 1,000 miles away. And they tracked it on the radar until it got to the mountains, the Rocky Mountains, which are really high mountains, and they thought, well, that's okay. It will just crash into the mountains, there's no one there. They next picked it up on radar the other side of the mountains, so it had on its own managed to get through the Rocky Mountains, and according to the specifications for the drone, it wasn't capable of doing that. So it had found some way of actually going over above the high altitude it was designed to go, and down the other side. Eventually it crashed because eventually it ran out of fuel. But if we don't give them good objectives and control them, they're going to be potentially quite dangerous.
그래서 자율 시스템의 사전적인 의미를 살펴보면 어토노미라고 하는 것은 정보를 바탕으로 한 강제적이지 않은 결정을 얘기를 하는 거고요. 따라서 오토노머스 시스템이라고 하는 것은 정보를 바탕으로 스마트하고 인텔리전트한 결정을 내릴 수 있는 시스템을 얘기하고 있습니다. 여기서 자동 시스템하고 오토노머스 시스템하고는 분명히 차이점이 있고요. 자동 시스템은 인풋에 따라서 항상 똑같은 결과를 주는 거지만 오토노머스 시스템은 그거보다는 좀 더 똑똑한 결정을 할 수 있는 시스템을 얘기를 하고 있습니다. 그리고 오토노머스 시스템을 위해서는 중요한 점 중에 하나가 이제 목적을 줘야 한다는 점이고요. 그 목적을 주지 않았을 경우에는 말씀해 주셨던 예제는 미국에서 최근에 가장 큰 드론 중에 하나가 예상치 않은 상황에서 목적이 없었을 때 없어진 시나리오에 대해서 말씀을 해 주셨습니다.
And here we can see some examples of autonomous systems that are actually already working. We have lawnmowers that will cut our grass, vacuum cleaners. I guess some of you may have automated or autonomous vacuum cleaners that you just leave in your house to clean the floor. We were just talking about drones. Autonomous cars, obviously everyone knows about. In countries with good economies, we have autonomous tractors and farm equipment because we can't afford or don't want to pay for the drivers for doing really simple jobs. We have astronomical systems, so searching for life on other planets is being done using autonomous systems. Marine systems, although this is a surface marine system, in fact the most common autonomous marine systems are underwater systems. And of course here we've got a Mars rover, and if we have systems that we actually send millions of miles away where it takes maybe 20 minutes to actually communicate with them, we actually have to give them some autonomy, otherwise they can't cope in that situation.
네, 현재 나와 있는 여러 가지 자율 시스템에 대해서 말씀을 해주셨고, 뭐 당연히 청소기, 자동차 이런 거 말고 여기 뭐 해양 분야나 아니면 왼쪽 아래에서 보시는 거는 외계 천체를 발견하기 위한 망원경 또는 뭐 마스에 올라가 있는 로버 이런 것들이 지금 사용되고 있습니다.
So the examples I showed you on the last page were all physical, because obviously it's much easier to get pictures of physical systems. But autonomous systems don't have to actually interact with their environment physically. We can also have purely digital systems. So down at the bottom here, we've got financial systems, and typically most of the financial markets now are being run. Over half of the trades are being done by artificial intelligence. It's used two ways. One is that it can work much quicker than humans. So it can do these nanosecond trades and make decisions in nanoseconds. Because if you wait longer than that, someone else makes the trade before you and the price changes. But also, they're being used in financial systems because they can make predictions based on big data. And if we give them lots of big data, lots of information about how the markets work, then they can make better predictions typically than humans can, because they see a bigger picture. Humans in the future will only gain anything working on these financial markets if they have special knowledge that is not available to the AI. And as time goes on, more and more of that information is just going to be immediately available to the AI, because if it's in the newspapers, if it's on the internet, the AI will have the information. So, an area where jobs will definitely disappear, and jobs at a really high level, really highly paid jobs. Most of the times with these systems, we're typically losing lower paid jobs because the systems are simpler. So if we look at the top here, well, with cars and trucks actually are more higher maturity autonomy than cars at the moment. So if we were looking for autonomous systems that were more advanced, we'd be looking at trucks, and trucks how they're platooning, trucks how they're deciding where to fuel, how often to fuel, because they don't want to lose too much time. But of course, if they find that they're coming close to a gas station that's got really cheap fuel, the AI will tell the truck this is a good place to stop. Because even if it's not empty, it will make more money by doing it that way. We were earlier talking about the drones. And in fact, ships and boats, the marine area is a large area. Trains have now started being created as autonomous systems. And in fact, the world's largest robot is a train, I think. There's a train in Australia that is used to carry ore from the mines to the port. And it's 2.4 kilometres long. So we have a computer system running a 2.4 kilometre long train. No human interaction needed. And it's been approved by the Australian government, and it works really well. When you try and take it to America, anyone care to guess what was the first thing that happened when they tried to take the autonomous train to America? Well, the union said, this is completely unsafe, you will always need humans. Yeah. So some countries have stronger unions than others. We talked about vacuum cleaners. We can go really small. We can all buy smart thermostats for our homes, where the thermostat actually keeps track of where we are. So it talks to our mobile phone, works out where we are. If we're getting close to the home, It warms the home up. If we get further away from the home, it cools it down. It measures and records how we often use the house and predicts ahead to when it needs to be warmed. In medical diagnostics, this year the American FDA, the drugs agency, just approved the first autonomous system for doing diagnostics. So this system actually can do diagnostics based on diabetes. So it looks at your eyes and predicts with an accuracy of greater than 90% whether or not you have diabetes. And it can be used by anyone. Anyone in this room could use this system. So all of the expertise about diabetes and looking at your eye is in the system. All we would have to do is push the person into the chair and make sure the system could see the eyes. How you use that information is then interesting, because if you start treating people purely based on an AI-based diagnosis and it goes wrong, we're not quite sure what happens. We know these systems, they've been measured, are actually better than the humans though. And we can put these systems everywhere. We don't have to train lots of experts in doing this diagnosis. And more and more of these systems will be built. We're already using the AI to do diagnosis of things like cancer. And then people obviously get involved to decide what gets done. But after a while, we're going to start getting AI in the medical area where the AI can actually do the operation. Already we use AI for operations because humans, even if they're the best human surgeons, jitter a bit when they're moving their hands. And we can use AI to actually smooth that out. And it predicts where the surgeon wanted the cut to be made. And the AI takes control. I'm sure you're all aware of smart buildings, smart cities, smart energy, smart water, etc. The list is endless. So we can't avoid autonomous systems. As engineers, what I think we should be doing is actually coming up with a systematic approach from the engineering perspective, the scientific perspective, on how to make them safer. If we don't provide options for government to do this, government will just allow the systems to go out with very little regulation. And that will be dangerous. There will be some disasters, and that could well set back the use of these systems by many years. And that, I think, would be bad. Because for most of these systems, they're better than letting humans do it. They're more efficient, they're more effective, and they will save money. And, as we'll see with the autonomous cars a bit later, they will save lives.
네, 그래서 자율 시스템이라고 하는 거는 이제 뭐 차나 승용차나 뭐 배 같은 물리적인 시스템 말고 지금 순수하고 디지털인 시스템들도 많고요. 처음에 들어주셨던 예제가 이제 금융 시스템. 실제적으로 지금 현재 전체에 이루어지고 있는 금융거래 중에서 50% 이상이 AI를 통해서 이루어지고 있고, 궁극적으로는 좀 돈 많이 받는 그런 직업들이 상당히 많은 위협을 받을 거라고 말씀을 하십니다. 그리고 지금 뭐 차나 트럭 이런 거에서는 현재 트럭이 상당히 진보된 상태고, 그 다음에 들어주셨던 예제가 이제 호주에서는 이미 정부의 승인을 받은 기차가 2.4km에 걸쳐서 지금 현재 주행되고 있고, 그 시스템을 미국에 갖고 갔을 때는 뭐 노조의 반대로 무산됐다는 얘기도 해주셨고요. 그 다음에 스마트 온도계에 대해서 말씀을 해주셨고, 스마트 온도계는 현재 지금도 누구나 구입해서 사용할 수 있다는 점을 강조를 해주셨고, 지금 의료 쪽에 관련해서는 이미 올해 FDA의 승인을 받은 당뇨병 진단할 수 있는 그런 시스템이 있다고 합니다. 그래서 아무나 이렇게 거기 시스템을 쳐다보기만 하면 시스템이 그냥 눈을 보고 그 사람 눈만을 보고 당뇨병이 걸려 있는지 안 걸려 있는지를 판단할 수 있다라는 거고요. 이제 이 상황에서 우리한테 중요한 게 뭐냐면은 실제 이 자율 시스템에서 내놓는 결과를 어떻게 사용할지가 굉장히 중요한 사항이라고 말씀을 해주셨는데, 엔지니어로서 우리는 이 결과에 대해서 좀 체계적으로 접근할 수 있는 그런 접근법을 만들 필요가 있고, 실제적으로 정부의 규제나 이런 거 없이 이 시스템들이 실제 시장에 배포되기 시작하면 상당히 안 좋은 그런 결과들이 많이 나올 수 있다라는 말씀을 해주셨습니다.
There are, however, some well-known failures, and you will all be aware of the Tesla failure from a couple of years ago, where someone died and their Tesla drove into the side of a truck. It was a bright sunny day, the truck was easily visible, but it was white. And when you looked at the sky was very light as well. And it appears that the sensors and the AI behind it thought that the truck was a bridge and drove into it. Of course, the driver should, according to Tesla, and the advice they give to all of their drivers is that they should be driving with their hands on the wheel, ready to actually control the car. This driver wasn't, because the driver had 20 seconds to see the truck and didn't do anything, just drove into the truck. And it appears that he may have been watching a video, because there was a video playing in the crashed car when they actually caught up with the car. The Yuba Crash this year, I don't know if you've seen the video, but if you watch the video, it is really clear that there is someone walking in front of the car. And you can't imagine how the system missed it. But of course, you can't imagine also how the safety driver missed it as well, because there was a safety driver in the car. But of course, we now know that the safety driver wasn't actually watching what was going on. I think they were looking at their phone, unsurprisingly. Because one of the things we know about autonomous cars is that if we put autonomy into a car and then we put a human in there to act as a backup to that autonomy, it doesn't work. Humans are no good at concentrating on things when they're only called into action once in every, well, some tiny, tiny percentage of the time. They get bored very quickly. So one of the things we know from these two examples, that if we're going to put autonomous cars on the road and we want them to be safe, we can't rely at all on the humans. We need to jump straight to a level, which would be SAE level 5, where all of the autonomy is taken care of by the computer. If we have to rely on the humans, it just won't work. Because people have just not got the concentration. And the other thing is, once the car drives them on 5-10 journeys safely, they think it's completely safe. On the internet, there are lots of ways shown how to trick the Tesla cars into thinking you're holding the steering wheel. The current favourite is jamming an orange against it, because apparently that is like a human hand. But while we're getting that, it's going to be unsafe. This third example is from quite a long time ago, but the court case which blamed the collision avoidance system, which had very limited AI, more an automatic system. But this one gives an example of It isn't just the people in the accident who are affected. In this one, two aircraft flew into each other. Initially, the air traffic controllers, who were Swiss, were blamed for the accident. Now they believe it's more likely that the collision avoidance system actually went wrong. And we know that with the collision avoidance systems, especially the early ones from 2002, the pilots found them very difficult to understand. They weren't sure if the collision avoidance system was higher priority than the air traffic controllers. So the pilots thought, well, air traffic controller, human telling me to do something, collision avoidance system, computer telling me to do something differently. Which one would you believe? Well, we now know you should believe the computer. The guidance to all the pilots is obey the computer. It's much more likely to be right than the air traffic control human. The actual air traffic control human involved in this was a secondary casualty, because about 71 people died in this accident, and the husband of one and father of some of the victims on one of the aircraft, about a year after the accident, tracked down the air traffic controller and murdered the air traffic controller. Even though it appears now, it may not have been his fault.
네, 그래서 뭐 자율 시스템이 실패한 여러 가지 유명 사례들을 말씀해 주셨는데, 첫 번째, 두 번째 같은 경우에는 자율주행 차에서 뭔가가 잘못돼서 실제적으로 그 탑승해 있던 사람이 죽는 그런 사고가 발생했던 경우들인데, 두 경우 다 실제 그 탑승해 있던 탑승자가 무언가를 할 수 있는 상황이었음에도 불구하고 딴짓을 하느라고 뭔가를 하지 못했던 상황들입니다. 그래서 결론적으로는 자율주행 시스템을 위해서는 사람이 백업으로 필요한 그런 단계를 건너뛰어서 완전히 자율주행이 가능한 단계로 넘어가는 게 좋다는 말씀을 해주셨고, 세 번째 같은 경우에는 이제 예전에 있었던 그 관제사하고 실제 그 충돌 회피 시스템 간에 서로 다른 의견을 줬을 때 누구의 의견을 듣는 게 과연 옳은지에 대해서 얘기를 해주셨는데, 이제 와서 결과를 분석을 해보니까 컴퓨터를 믿는 게 관제사를 믿는 것보다는 좀 더 나은 결과를 가져왔을 거라는 말씀을 해주셨고, 마지막에는 결국에는 실수를 했던 관제사를 비행기에 있는 누군가의 가족이 찾아가서 결국에는 복수를 했다는 얘기를 해주셨습니다.
I mentioned earlier about we now use AI for the majority of our trading on the stock markets, and because of that we're seeing where the AI systems interact with each other, them causing crashes in the stock market where they all try and do something at the same time. Because the difference in time between one system reacting and another system is so small that they all react at the same time, which can then plunge the stock really fast. And that means the regulators are actually having to put in circuit breakers. And in the last day, 2 days, we've seen the cryptocurrencies crash by 15%. That could well be because AI now, they all cancel each other out on the stock markets, but cryptocurrencies are being still largely traded by humans. And some people have started to use AI to trade cryptocurrencies, and now we're seeing crashes in those areas as well. We've seen examples where Google have used their AI to provide information on who should be given jobs, on whose CVs they should be looked at, and only in the last week Google have removed a system that was telling people, look at these CVs, throw all the rest away. And when they looked at the CVs, they found no women were actually ever in the list of CVs, because the AI had learned that the people training it always chose men for the jobs. And of course, if they all train the AI system to always choose men, the AI system will always choose men. And it will get worse and worse. And in America, they have some AI-based policing. They use AI to decide how long people should go to jail. It looks at their record and it predicts if they're likely to reoffend. If they're likely to reoffend, it gives them a longer sentence. They also use AI to decide where to send the police, because they don't have enough police. And what they found is they always send them to the poor black areas. But when they actually study it, they find actually those poor black areas aren't necessarily where most crime is. So the AI has learnt the bias of the police, which is to always blame the black people. So we have to be very careful with these systems.
네, 그래서 뭐 주식 시장에서는 지금 실제적으로 대부분의 거래가 50% 이상이 AI를 통해서 하고 있기 때문에 워낙 반응 시간들이 다 똑같으니까 어떤 특정한 정보가 주어졌을 때 한꺼번에 확 몰려서 서로 캔슬링 아웃하는 그런 현상이 발생할 수 있기 때문에 그런 거를 방지하기 위해서 이제 뭐 서킷 브레이커 같은 것들이 필요하다는 얘기를 해주셨고, 구글의 예는 이제 실제적으로 어떤 사람이 고용을 하기 위해서 구글 서치를 할 경우 해당 포지션이 좀 돈을 많이 주는 그런 포지션이면은 계속해서 사람들이 남자들만 뽑다 보니까 이제 여자들 없이 여자들을 다 제외하고 구글 서치 엔진이 알아서 남자들만 걸러주는 그런 현상이 발생한 적이 있었다는 얘기를 해주셨고, 미국 같은 경우에는 이제 AI를 통해서 재판을 하게 되는데 그 경우에 AI는 이제 재범의 확률, 그 범죄를 다시 일으킬 확률을 가지고 그 사람들의 형량을 판단하게 되는데, 그때 흑인들한테는 매우 불리한 판결을 많이 했다고 합니다. 흑인들이 재범을 할 가능성이 매우 높기 때문이죠.
So what does an autonomous system framework look like? At the highest level, it looks something like this. We get information from the environment. We get information from people telling us what the system should do. That information goes into the sensing. We try and make sense of the information we're getting into the system. The system then does some decision making. If it's an autonomous car, do I turn left? Do I turn right? Do I stop? And then finally, we've got the control. Actually sending the messages to the actuators so that things happen in the real world. If we're looking at a financial system or a medical system, then at that point it's not actually going to actuators. The actuators are people. It's information being sent to people who will act on the results of the system. And what we can see is that we obviously have a number of choices about how much AI we put into such systems. And as a basic minimum, we have to put AI into the image processing. We know that image processing doesn't really work with any other technology. So we have to put AI in there, really. Decision making is normally better done in a probabilistic manner, because there are so many decisions to make, we can't check every possible one, in which case we probably have to have AI across there as well, in which case we're at this level. The control is less sure. The control we can get away with using traditional techniques. So most of the autonomous cars we see are probably there or there and don't cover the whole three. Some of them do. NVIDIA, who make sensors and processors specifically for autonomous cars, did a small experiment, and their small experiment was 72 hours. They fitted a car really simply, just with video cameras, and they connected actuators to the steering wheel and sensors to the steering wheel. So they drove this car for 72 hours, and they then taught the AI. After 72 hours, the car could drive long distances on the routes it had been taught. It could steer. It couldn't do any of the speeding or braking, but it could keep on the road. After, what, 3 days worth of training. And that system was across the whole thread. So potentially, it's quick and it's easy.
네, 그래서 자율 시스템이 위에서 보는 것과 같은 프레임워크를 주로 가지고 있는데, 뭐 AI를 어느 수준으로 적용할지는 뭐 밑에서부터 1, 2, 3번이 있다고 했을 때 최소한 1번은 돼야 되고, 대부분의 현재 개발되고 있는 자율주행차는 2번 정도 수준에 머물러 있다고 합니다. 그리고 들어주셨던 예제는 엔비디아에서는 이제 3번 접근법을 가지고 72시간 만에 알아서 스스로 이 핸들을 조작할 수 있는 차를 만드는 데 성공했다고 하십니다.
So I've been using the term artificial intelligence. In fact, in these systems, typically what we're using is known as deep learning. So deep learning is a form of machine learning, and machine learning is just one of the many forms of artificial intelligence. And if we use deep learning, as it says there, we'll end up with a non-deterministic system, and we create what's known as a deep neural network. And a deep neural network, at a very abstract level, looks like this. And it's called a deep neural network because it has a number of layers. So that's what makes it a deep neural network. I'll actually explain a bit later in more detail how this works when I explain how I think we can test it.
네, 그래서 보시는 그림 중에서 딥러닝이라고 하는 거는 머신러닝의 일부인데, 가지는 차이점은 이제 결정론적인 그런 접근법이 아니라 확률적인 접근법이기 때문에 딥러닝이라고 한다고 하시고, 그 다음에 뉴로 네트워크 같은 경우에는 여러 개의 계층을 가진 지금 보시는 것과 같은 그런 그림으로 표현될 수 있다고 하십니다. 자세한 설명은 차후에 다시 하신다고 합니다. 뒤에서.
So here's a really simple example of how we would do machine learning. We have to give it a training set. And the training set, let's imagine we're doing image classification, so we want our neural network to be able to recognize, in this case, buoys, trees and pumps. So for it to be able to do that, we have to give it lots of images, and we have to label the images so it knows which is which. And then once we've done that, we can generate the neural network. So the artificial intelligence framework will generate the neural network from analysing that information. Now, once we've got the neural network, we can then give it an image, and in this case, if everything's working okay, the neural network will tell us it's a buoy, because even though this image doesn't appear in the training set, the neural network has enough information there to infer that this is a buoy.
네, 그래서 보시는 예제는 부오이, 트리, 펌프로 이루어진 세 가지 요소를 가진 트레이닝 세트고요. 이 트레이닝 세트를 통해서 뉴럴 네트워크를 형성하게 되면 차후에는 저기 트레이닝 세트에 포함되지 않았던 저와 같은 그림을 주더라도 시스템이 알아서 이제 부오이라고 판단할 수 있다고 합니다.
So, looking at it in slightly more detail, we have to choose how we're going to generate the neural network. We choose that with the model and parameter selection up here. This is really complicated. This is the area where people get paid lots and lots of money, and there are very few people who are really good at it. If we're considering it from a testing perspective, that's okay because we don't have to get involved in that. We just have to test it. But we need to be aware that this is really complicated, and it's really easy to make mistakes and not choose the optimum set of parameters and not choose the optimum model. Now, a deep neural network is one particular model, and there are variations of that, and it depends what you're asking the system to do, which would depend on which model you chose. So if, for instance, you're looking at two-dimensional data or three-dimensional data, which would be images, black and white or colour images, then deep neural networks are really good. But there are other types of AI that we could come up with here that would depend on what we were trying to do. So we need to be sure that we're choosing the right ones. We then feed it the training set, and it generates a neural network. Of course, we don't trust it just like that to work, so we have a test set as well, which is a separate set of data. If it's doing images, this is a separate set of images, all labelled so we know what they are, and we then feed those through the neural network, and that will determine the accuracy of the system.
네, 그래서 뉴럴 네트워크를 만들기 위해서 이제 저 모델하고 파라미터를 선택하는 게 굉장히 어렵고 굉장히 돈을 많이 받는 사람들이 하는 일인데, 알아야 될 사항은 그 사람들이 실수를 할 수 있다는 것을 충분히 인지를 하고 있어야 된다고 말씀을 하시고, 그 모델하고 그 파라미터가 선택되면 거기에 따라서 이제 필요한 뉴럴 네트워크를 만들게 되고 트레이닝 세트를 넣음으로써, 그래서 만들어진 뉴럴 네트워크는 테스트 세트를 가지고 얼마나 정확한지 테스트하게 됩니다.
So we can build a self-learning system using this technology. So imagine we're going to put it in a car slightly in the future. So we've got our neural network in the car, and as it's a self-learning system, we want it to learn from its experiences. So as it's making decisions, it's looking at the outcomes of those decisions. That creates experiences from it. It then can use that for training. It can then create an improved neural network, hopefully. And once we've got an improved neural network, obviously we have to test it to make sure that it works, but we would have to test it very quickly because the car's driving around on the streets, and that then updates the neural network in the car. So our neural network in the car is getting better all the time, and this sometime in the future is happening in real time. When I say sometime in the future, this is many years in the future. This is not what you're going to get in 2020 or 2025 from the current car manufacturers. This is more 20 years, 25 years into the future, because we are nowhere close to this technology yet, because we can't do this testing in real time, and we don't trust the frameworks to build a new neural network that is safe in real time either.
네, 그래서 뭐 당장 일어날 일은 아니고 앞으로 적어도 한 20년 후에 일어날 일이지만 궁극적으로는 저렇게 지속적으로 알아서 러닝하는 시스템을 만들게 되면은 시스템이 경험을 가지고 다시 트레이닝을 하고 주행 중에 알아서 런타임 테스팅까지, 실시간 테스팅까지 진행을 함으로 인해서 지속적으로 개선이 될 수 있는데, 뭐 중요한 점은 현재는 전혀 그렇지 않고 적어도 한 20년 후에는 저것을 목표로 한다고 하십니다.
Much more realistically, we're going to have cars that learn offline. So we've got lots of cars out there. We've given them all neural networks. They communicate via the cloud at a set time, perhaps. And so all of the cars are collecting their experiences. That goes back to the OEM. The OEM then uses those experiences to train an updated neural network. So this is close to what we think Tesla are doing at the moment. They're actually using the cars that are out on the streets to collect data and improve the systems.
네, 앞장에서 보셨던 거는 먼 미래 얘기고 지금 실제적으로는 도로에서 주행하고 있는 모든 차들이 클라우드를 통해서 경험 데이터를 보내면 OEM에서 그거를 가지고 업데이트된 뉴럴 네트워크를 배포하는 이런 형태로 진행되고 있고 지금 현재 테슬라는 이와 같은 모델로 하고 있을 걸로 생각된다고 하십니다.
And of course, once we've got this updated neural network, we need to do lots of testing because this is a safety critical system. So we do lots of offline testing. When we, as the OEM, are confident, we would do an update on a particular date and it would go out across the cloud. So we would do an over-the-air update to each of our cars to update their neural networks to the new, improved version.
그래서 오프라인 테스팅까지 진행하게 되면은 결국에는 뭐 특정한 날짜에 OTA를 통해서 클라우드를 통해서 각각 차들로 배포되는 그런 모습일 겁니다. 입니다.
A problem occurs though with this model if one of the experiences that we actually record from our cars tells us as the OEM that the system is dangerous. There's a situation not where we can make it more efficient or more effective, but where the experiences we get fed back tell us that the system is now dangerous. Because if the system is dangerous, we need to do the update really quickly. And now we have to make a really difficult decision because if we know the system is dangerous, do we leave all the cars running? Do we leave our million cars on the road still running, knowing that there's a bad system? Do we do some testing? If we do some testing, how quickly do we do it? Because if it takes us longer than a few hours, we're going to have to either leave the cars out on the road when they're dangerous, or we're going to have to tell the drivers you can't use the car. And that will be a really interesting thing to decide, to see what the OEMs do. My guess is the OEMs would make sure that they only classified the problems as being not dangerous, because it would be very bad if they had to stop all the cars running.
네, 그래서 저렇게 취합되는 데이터 중에서 실제적으로 안전에 치명적인 게 있을 때 상당히 어려운 결정을 해야 된다는 말씀을 해주셨고, OEM의 입장에서는 그런 문제가 발생했을 때 과연 차들을 멈추는 게, 전체를 다 멈추는 게 맞는지, 아니면 운전자들한테 얘기를 안 해주는 게 맞는지, 거기에 대해서는 좀 생각이 필요하다는 말씀을 해주셨습니다.
Okay, so let's look at where the mistakes are most likely to occur in machine learning and where, therefore, we should be doing the testing. So, fairly obviously, we have to give the system enough training data for it to learn. And when we generate that training data, we want lots of training data. We want the training data to be representative of situations that will happen in the real world. Otherwise, we will bias the system. There's great temptation to use all of the data that we have in the training set. Because if we do that, we now have no test set. Because these two sets have to be completely independent. Because obviously if we train it with data and we give it the same data to test it, it will work. So we have to make sure these are absolutely different. Now up here it says, are the sets based on real or synthetic data? And surprisingly to me, actually, if we're trying to train a system, often it's best to train it with synthetic data. Because with synthetic data we can take out all the noise. Now we base the synthetic data on real data, But when we're actually doing the training, a large percentage could well be synthetic. Of course, we probably don't want to use synthetic data in the test set. So again, we have to be really careful with our configuration control, making sure that all of these sets of data are really carefully labelled and not allowed to get mixed in with each other.
네, 데이터를 선택할 때 굉장히 중요하게 봐야 될 게 트레이닝 세트에 충분한 데이터가 있는지, 그리고 트레이닝 세트하고 테스트 세트는 당연히 두 개가 달라야 된다는 말씀을 해주셨고, 트레이닝 세트하고 테스트 데이터에 과연 인조적인, 가짜 정보를 사용해도 되는지, 거기에 대해서 의견을 주셨는데, 의견은 이제 트레이닝 세트에는 당연히 신테틱한 데이터가 좀 들어갈 필요가 있다는 말씀을 해주셨고, 테스트 쪽에서는 당연히 진짜 데이터를 쓰는 게 좋다는 말씀을 해주셨습니다.
And of course, there are now several businesses set up already, have been set up for some of them for several years, and those businesses' job or whole reason for being is creating this test data and this training data. And of course, it's really easy to make mistakes when you're doing that job. So imagine that we get given the task of actually labelling objects from pictures, because we look at the images, we label them. This is our job. We can do it at home, so it's a really easy job in terms of commuting. We just have to label the images because these images are going to be used as the training set. So this says trunk. Great. And then we get a more complicated image, and I don't know what that says, whatever it says. Oh, let's actually put another trunk in there. So now we've got two trunks, and we're driving past a zoo, so we've got an elephant there as well. And of course there are trees everywhere by the sides of roads, so that's quite common. And we want, if it's an autonomous car, we want it to be able to recognise tree trunks, because they're really things we want to avoid if we have to crash. Our passengers will die. Now, imagine you're a Korean company and you're labelling images and these are going into a training set. And you're selling this training set to US because they need as much training data as possible. Now, you would have a clue that there was a slight problem when you have got the same words for these. Because if when you sent it off to your client and you just used some translator program, how will it know the difference between this one and this one? Because maybe we haven't given it the context. It could work. When it actually got to the United States, it would look like this. Is that any use? In English, the same word for all of those things. So the opportunity for mistakes, not just in the labelling, because we reuse the same word, but opportunity for mistakes in translation is enormously high. We have to be really careful when we're creating this classification. And we have to be very careful when we train the people to label things, so that they label things exactly as we want them to be labelled and exactly as we want the system to be able to use those terms. So if they're labelling lines on the road, we have to make sure they're labelling exactly the right place, that they're not getting tired and just clicking on the curb, because the curb at the side of the road is different from the line by the side of the road.
네, 그래서 뭐 예를 들어서 저희가 그 트레이닝 세트를 위한 데이터를 레이블링하는 데이터에 이름을 붙이는 작업을 하고 있다고 가정했을 때 이제 뭐 언어의 차이가 가져올 수 있는 문제, 또는 뭐 아까 보셨다시피 지금 그림에서 보시는 것처럼 여러 가지 단어가 똑같은 단어로 사용될 수 있는 그런 경우를 고려해야 되기 때문에 레이블링 작업을 할 때는 굉장히 유의해서 정확하게 무엇이 필요하고 무엇을 원하는지를 알고 진행해야 된다는 말씀을 해주셨습니다.
So, as from a testing perspective, we need to look at this training set and make sure that it's generated safely, that it's generated without bias. And I gave you an example of that with the black police, or police and the black people in America. Underfitting, overfitting, extraneous outliers. We've got to make sure it's truly representative.
네, 그래서 데이터를 만들 때는 뭐 편견이 없는지, 또는 뭐 너무 지나치거나 너무 부족하지 않은지, 아니면 관련이 없는 데이터가 없는지, 이런 것들을 다 유의해서 데이터를 만들어야 됩니다.
And here we see an example which could be urban myth, but this is data bias. So we've given the system pictures of tanks. The idea is that the Americans wanted an AI system that could recognize American and Russian tanks. Could be useful, I suppose. And they gave it information like this. Seems reasonable. It should be able to learn from that. Tanks are quite easy to spot. They're quite unusual. And then they give it this picture. And it says, well, that isn't a tank. Why isn't it a tank?
왜 탱크가 아닐까요? 데이터 편견에 대해서 얘기를 해주시고 계신데, 이제 시스템한테 위에 네 가지 그 탱크를 트레이닝으로 줬는데 결론적으로 저 밑에 맨 왼쪽 아래에 보시는 거는 시스템에서 탱크가 아니라고 했습니다. 아니라고 판단한 이유가 무엇일까요?
Clouds. Absolutely. Up here, the Americans sent out people to take a picture of tanks, and of course, if you're being sent out to take a picture of tanks, you do it on sunny days. You don't do it in the rain because you're going to get wet. So up here, we have pictures of tanks with blue sky. Here, we've got a picture of a tank with cloud. The neural network has learned to use the sky to determine if it's a tank. The sky is noise. This is the signal. So our signal to noise ratio is wrong. For it to work, we have to give it pictures of tanks with clouds as well. Otherwise, it will use other information to try and get the result. Yeah.
그래서 뭐 탱크를 저렇게 맑은 하늘에 딱 맨날 하다 보니까 이제 구름이 있는 날은 탱크를 못 알아보고, 그렇기 때문에 결론적으로는 트레이닝 세트에 저 탱크가 아니라 뭐 주변에 노이즈라고 볼 수 있는 다른 요소들이 뭐 여러 가지인 상황을 줘야 될 필요가 있다고 말씀하셨습니다.
Another example of an incomplete training set. We're trying to train it to be able to identify swans, and we give it lots of pictures of swans. And then well, 200 years ago, everyone who hadn't visited Australia would say that this was right. Only after we visit Australia do we realise that actually you can get black swans as well. But if we don't give the neural network all the information, then it will come up with bad decisions.
네, 요 예제는 이제 불완전한 세트를 얘기를 하는 거고, 실제적으로 200년 전에 호주에서 검정 스완이 발견되기 전까지는 뭐 저게 컴플리트하다고 볼 수 있는데, 지금은 저게 인컴플리트하다고 보는 게 맞다고 얘기하십니다.
So we need Also, as testers, to make sure that this test set is good enough. We should have systematic ways of creating the tests. We should have positive tests and negative tests. We need to cover the boundary conditions and the corner cases. And we have special bugs in neural networks. We also need some adversarial tests, which I'll talk about a bit later.
네, 그래서 테스트하기 위한 테스트를 만들 때 이제 체계적으로 만드는지, 포지티브하고 네게티브한 테스트를 다 하는지, 뭐 경계를 다 테스트하는지, 그리고 저 마지막 거는 이제 이 상황, 이 자율 시스템에 좀 특수한 건데, 뭐 적대적인 테스트도 충분히 하고 있는지, 적대적인 테스트에 대해서는 뒤에서 좀 더 추가로 설명하실 예정입니다.
As with traditional systems, if it's not safety related, we can live with commercial frameworks, commercial tools. However, if we're going to build autonomous systems that are safety critical or safety related, then the tools we use to build those autonomous systems should be certified. They should be of a certain quality. So when we actually look at the model chosen, the parameters selected, there would have to be documentary evidence that they were chosen sensibly. And the tool we use here, which obviously is extremely important, would need to be qualified. If we use a tool to build any part of software for a safety critical function in a car, we are only allowed to use qualified tools. At the moment, there are no qualified tools for building neural networks. But there are lots of manufacturers saying, oh, we've got software running in the cars, and the cars are going to be autonomous. But that software has been created by tools that we don't trust. We can't trust because we haven't got enough information about them. So we would need to actually improve in this area.
그래서 자율 시스템에 관한 모순 중에 하나인데, 딜레마 중에 하나인데, 이제 아무래도 안전에 치명적인 시스템이다 보니까 그것을 만들기 위한 여러 가지 도구들이 그래도 어느 정도 상용 수준이 아니라 어느 정도 인증을 받은 툴들을 사용해야 되는데, 실제 지금 자율주행 시스템은 많은 상황인데 그것들을 만들기 위한 툴들 중에 뭐 인증되거나 확인된 그런 툴은 없는 상황입니다.
So we've got a lack of high integrity machine learning frameworks. We've got a lack of software libraries. We don't write all of our software from scratch anymore. We reuse over 90% of it. However, the manufacturers, the OEMs and the people like Google, Waymo and Uber and Tesla aren't using those because they're not available. And that's partly because there are no standards telling them what they should do. So we need standards to actually tell them what to do in this situation. Also, as soon as we have more than one autonomous system interacting with another autonomous system, we know there's the potential for problems. I've already mentioned the problem of stock market crashes, where interacting AI systems have caused the crashes. Imagine if we've got two autonomous cars coming towards each other and they're both trying to make the same turn. One's from one manufacturer, one's from another manufacturer. Now we've got two interacting autonomous systems. If they're not communicating with each other, and if they don't know what the intentions of the other autonomous system are, the potential for causing a disaster is quite high. Or an accident, anyway. And that's just with two. You can imagine one of the junctions in Seoul where we had 30 or 40 interacting autonomous systems, all trying to go through the junction at the same time. It could potentially be a disaster.
네, 지금 자율 시스템 같은 경우에는 공통적인 소프트웨어 라이브러리를 사용하는 적이 없고 그런 것들이 없기 때문에, 그리고 어떤 특정한 표준을 따라서 진행되는 경우도 없습니다. 그래서 들어주셨던 예제는 이제 교차로에서 두 개의 자율주행 차가 서로 똑같은 턴을 하려고 했을 때 어떤 상황이 발생할지, 또 어떤 문제가 발생할지에 대해서도 충분히 고려가 돼야 되고 표준적인 무슨 접근법이 필요하다는 말씀을 해주셨습니다.
Now, autonomous self-learning systems are probabilistic. Because they're probabilistic, they're non-deterministic. Now, from a tester's point of view, having deterministic systems is really quite important because they are much, much easier to test. Even the complex deterministic systems are far easier to test than non-deterministic systems. And I'll show you why. This is an ideal deterministic system, so it does what it's supposed to do. It's perfect. I give it some test inputs, and I get some expected results. I get some actual results, but they match the ones I expected. It's a deterministic system, so if I run that same deterministic system again at some later time, I get the same expected results. Makes my testing easy, because I generate test cases that say this is the test input, this is the expected result, and I can rerun that test case many, many times. So once I've designed that one test case, it works hopefully forever until I change the system. If I change the system, I hit a problem, and we all know this problem. And we do things like impact analysis to try and determine which parts of the system are affected. And then when we do regression testing, we make sure that we have different tests. But the basic point about getting the same expected results is that if I run a system once with this set of test inputs and it works, any time in the future, I believe the system will work. That means this test case is valuable for me for giving me confidence that when it goes into the real world, it will actually work, because it will do exactly the same thing. So having this determinism not only makes regression testing better, it allows me to reuse test cases, but it also gives me absolute confidence in use. The point of me doing this testing is to get that confidence.
네, 그래서 자율 시스템 같은 경우에는 결정론적인 시스템이 아니고 확률적인 시스템인데, 우선 결정론적인 시스템 같은 경우에는 항상 동일한 인풋에 대해서는 동일한 아웃풋을 줄 거라고 기대할 수 있는 그런 시스템을 얘기를 하고, 테스트하는 입장에서는 동일한 인풋에 대해서는 항상 동일한 그 아웃풋이 나오기 때문에 해당 시스템에 대해서 어느 정도 자신감을 가지고 접근할 수 있다는 것을 먼저 말씀을 해주셨습니다.
If I have an autonomous system, it's non-deterministic. If I have an autonomous system and I run it at one time, and then run it again with the same tests, I get different results. That means my test case, if it's a simple test case, is no use to me in the future. That means I have to have smarter test cases. The test cases have to have some tolerance. And if I'm going to have test cases with tolerance, if I want a level of confidence, that actually means I have to generate many more test cases. So if I'm testing a non-deterministic system, I have lots and lots of test cases, more than I have for even a complex deterministic system.
네, 그래서 비결정론적인 시스템을 테스트할 때는 항상 결과가 동일하지 않기 때문에 적용하는 테스트 케이스가 훨씬 좀 스마트하고 광범위해야 되고 훨씬 많은 수의 테스트 케이스가 있어야지 일정한 수준의 자신감을 가질 수 있다는 말씀을 해주셨습니다.